I have some comments on that about what I discovered.
Okay, so today it's April 13th, 2019, and this is John Chappell Natural Philosophy Society. So, Harry, what do you think of this announcement of a black hole? Let me see if I can go find a picture of that.
Well, what did they say? Let's go back. What do you think they said? What do you think it is?
Well, they're clearly saying that using this series of 8 telescopes, which they call the Event Horizon Telescope, they unveiled the very first image captured of an actual black hole.
Well, that's kind of what they were talking about that I heard was they were claiming that it was a photograph. A lot of the news sources were claiming that it was a photograph, and so that confused things. It's essentially nothing more than a radio map.
Yeah, I was wondering about that. So the Event Horizon Telescope, is that like a series of radio telescopes? Is that what that is? Because I find it
yes, it is.
I find it interesting, just a complete dearth of information on what this thing is. So, like you said, it's not. Well, it looks like
misleading is the news people were reporting it as a photograph of a black hole, or the word image I think got translated into photograph.
Well, it is a photograph. It would be fair to say that
it's not. It's a radio map,
as opposed to I don't know, like lines on a graph. I guess that wouldn't be a photograph, but it's been rendered in such a way that it appears to be like a picture that might be taken from an optical telescope.
Exactly. That's what, and a lot of people got confused by that in the discussions that ensued.
Well, let's look at it. So this is the Event Horizon Telescope website here. Let's see here. Let's shut off our cameras here to save bandwidth. Here we go.
You see a scale on there anywhere?
I don't see it, but they were saying that what we're looking at there is bigger.
Where's the scale? Where is there a scale that says, show me the scale of the photograph? Is there like centimeters per cubic light year, or anything on there?
I don't think so. Not
well, see, that's another misleading aspect of it.
They say. Well, I read that image that you're seeing there is bigger than our current solar system. So that gives you some idea of the scale. This means that black part.
Yeah, but why don't they publish a picture with a scale?
So this is astronomers capture first image of a black hole. So this is an array of
now, here's another thing you'll find out if you go to other published publications. They'll say it's a black hole candidate. Somehow the candidate disappeared.
Well, this is from
the horse's mouth. A picture of what they think could be a black hole. More misleading information.
So they're saying the image shows a bright ring formed as light bends in the intense gravity around the black hole. It is 6.5 billion times more massive than the sun.
So assuming that it's a black hole, which they're not claiming that it is, they're calling it a black hole candidate, which says to me that it's just something that they speculatively think could be a black hole. So they went from saying it was a black hole candidate to now they're saying it's a black hole. So it says first image of a black hole, right? That's completely misleading.
Well, it could be, I guess.
Are they claiming?
Why didn't they say?
Sorry, are they claiming that they actually were looking for this, or that they just came across it and they said, "Goodness me, what's that? We better look into it."
No. They spent years processing this data. They've been working on this for several years, and this is their claimed result. It's really not. It's not a photograph. It's a highly processed map of a radio using, as I understand it, millimeter wave interferometry, because there's no way. M87 is really way the hell out there. I mean, it's a distant galaxy, way, way, way far away from Earth. It's really pretty far away. I mean, this isn't even in the Milky Way.
Well, there were some
galaxy in the Virgo cluster that's, you know, I don't know how many million light years away it is, but it's pretty far.
Well, I kind of like their here, which is that they say.
Were they specifically looking for M87 or whatever it is, or were they looking at other galaxies or Messier objects?
I think that the fact that it took them years to process the data to get to this point tells us that the amount of time that it takes to do this sort of thing is apparently there's a lot of different groups working on it, and they had to collaborate between the different groups. And I don't know, there's a number of papers on the internet that you can look at. And I looked at the paper where they talk about how they process the data. It's completely incomprehensible. I mean, it doesn't really mean anything to anybody who's not an expert.
I mean, I'm kind of wondering what they mean by forged. I mean, if as a computer scientist, I know I can make anything look like anything, really. And if I were to just biasly process any amount of data, I could make any region appear dark and any region I want to appear light, depending on how I do the mapping. And I could easily create anything that looks like that from a picture of Mickey Mouse or whatever. It wouldn't matter. So you got to wonder whether we're dealing with that sort of thing, and that this whole enterprise was designed to find these things, you know, much like Lego. And,
well, let's go back to what a black hole is. Okay, a black hole is supposed to be a collapsed star, meaning, and I forget what the Chandrasekhar collapse criterion is. I think it's 1.4 solar masses or something like that. I forget what the detail. Anyway, so they do these calculations, assuming that special relativity is correct, which is kind of a big assumption, and given the controversy, and then assuming that general relativity formulated based on special relativity is correct, and then you know, based on, you know, these theories that they developed, then they say, well, above a certain mass, the star collapses and forms what's called a black hole, okay, which is basically a well in the gravitational space-time. Okay, so this isn't that. Follow what I'm saying here?
this isn't that. What is the that you're talking about?
Okay, so around 2000 or so, they decided that that there's what's called a supermassive black hole at the center of galaxies. Now, this sort of thing has been known for a long time, what are called the nuclei of galaxies, and they're what called active galaxies. There's a number of different types of active galaxies, lots of different varieties. There's radio galaxies, there's active visual galaxies. There's lots of different types, and there's a classification of different types of what they call active galaxies. So they decided that that because by looking again, here's where the bugaboo comes in. They're looking at the velocity at which stars revolve around the nucleus. Remember, this is the bugaboo that led to the missing mass and the dark matter problem, they decided that there had to be this supermassive gravitational object at the center of galaxies, which technically is called the nucleus. And from that, since they decided that this thing had 10 million solar masses or whatever the number is, they decided it had to be a black hole, because theory says it's got to be a black hole, because anything that massive, okay, can't be gravitationally stable and has to collapse. So it's all about theory. So essentially they're speculating that that's the center of M87, which is a gigantic elliptical galaxy in the Virgo cluster, has to be a supermassive black hole. So essentially now they've said that they've made an image of a black hole, but if you look at the technical paper, it says it's a black hole candidate, not a black hole. So it's a black hole.
A candidate. So I found their picture here. This just looks like the black hole from the movie Black Hole, where I guess they're imaging this swirling gas that's falling into the black hole. Although, would it fall in the shape of a disk like that? I guess it would have to be pretty coincidental that the disk just happens to be pointing at Earth to take such a nice little picture there that the middle is dark.
Well, essentially, anything that's twirling around like that, you're going to get this flattened disk around it. I mean, that's, why they think the solar system is in a plane.
I don't know. Why did they think the solar system is in a plane? I mean, that's still not clear.
Because the spinning around causes it to flatten out. That's one of their standard. So, when they did the formation of the solar system, they said as it rotates, it flattens out to form a disk. And then the material in the disk sticks together or clumps together and forms planets. That's their theory.
Yeah, they call that the accretion disk.
Correct. Couldn't think of the name of accretion disk. Okay. Anyway, so that's what the claim is. But the issue is they're just saying that this thing that's at the center is a black hole. Why are they saying it's a black hole? Because theory says that it's too massive to not collapse on itself gravitationally. So if you believe the theory of gravitational collapse, which they teach, which is Einstein's theory of general relativity, since this thing is big, mass, a lot of stuff in there in a small space, then it has to be a black hole. So anything that's got a lot of mass in a small space is by definition, according to them, a black hole. So a black hole is really nothing more than a lot of mass in a small space.
Well, I would say that's probably fair. You don't think that's fair?
I didn't say it wasn't. I'm just saying calling it a black hole is a theoretical that's based purely on theory.
Well, it would seem that if they have a picture of it, then it's more than just theory now. I guess that would be the main point, right?
Well, they would like you to believe that, but they've created several frauds in by claiming that it's a black hole when it's not a black hole. It's only something that they think might be a black hole.
Well, I don't know. That's kind of a fine point, isn't it? That's the way things are in science. We have a hypothesis and we match it to the best available data.
You would think that you ought to be honest about it. Why aren't they being honest about it and telling us that they're only suspecting it could be a black hole? But no, they're not saying that. They're saying it is a black hole.
Well, maybe that's just an interpretation of the media. You did say that they said it was a candidate black hole in the actual science papers, right?
Well, you'd think that if they were being honest scientists, they would correct the media for that mistake.
Oh, no, the media, they don't deal with stuff like that?
Well, so essentially, what they do is they allow the media to create the fake science, and then the fake science becomes real science because nobody contradicts the fake science of the media.
Yes, it's certainly
Exactly.
better PR to leave out the word candidate. But I mean, I think theoretically they would say that black holes normally exist at the centers of galaxies, and presumably this was seen in the central portion. So hence their conclusion.
Yeah. I have a couple of issues with the picture. One is it doesn't give a scale. Why doesn't it give a scale? I mean, these are supposed to be careful scientists. Why don't they show me a scale?
Here's an interesting picture here. So they're saying that for the data we take only tells us a piece of story, as there are an infinite number of possible images that are perfectly consistent with the data we measure. Really? I mean, there's an infinite number of images possible?
Yes. So the bottom line is that they're picking one that looks like what they think it ought to look like.
Yeah, exactly. That's what these pictures are showing. That in the left-hand most picture, if it's just a fuzzy blob, that's unlikely, and that's probably what the data generally looks like. And then more likely is something that has like some kind of streamy stuff. And then very likely is exactly the same thing that they're exactly looking for, right?
Right.
So is it just a matter of finding the right algorithms such that it reveals the image that you're looking for?
Well, this is an example of what they call the selection effect, which is you find what you're looking for.
Yeah, so did they find it? Did they just find what they were looking for, and it just happened out of all the galaxies? I mean, I don't know how many they looked at, but maybe if you look at like,
I don't think they looked at anything other than this one.
If you look at 500,000 galaxies and you find one that has this looking picture in it, then you say, I found it, even though you didn't find that same thing in every other galaxy you looked at. Because it just happens to be that if you look at enough stuff long enough in a cloud, you'll see the picture you're looking for, right? So if you're staring up in a cloud and you're looking for pigs, you stare long enough, you will likely find one, right?
Well, that's how they're doing science now. They pretty much use the same technique on the LIGO, which is they have a model. Okay, they have a model of what the waveform should look like when it comes into the telescope. So what it does is it processes all this noise, okay, these waveforms, and it has an algorithm that looks for it's a match filter algorithm. It's what it's called, and that came out of electrical engineering. And in electrical engineering, we use the match filter algorithm because we know what the signal was that's being transmitted, because the guy at the other end is transmitting a signal, okay, and he does it according to a certain set of rules, okay. So the guy at the receiving end knows what the rules are that are being used to transmit the signal, and so he looks for, okay, based on these rules, processes the noise looking for a best fit match to the signal that he knows was transmitted. So you have to know what it is that you're looking for before you can find it.
But there's another picture of the accretion disk here. And they're saying that accretion disk will be brighter than all the other stars around it.
Okay, well, I think we've discussed this enough. I think it's kind of interesting how I thought it was a photograph based on what I'd read about it, and I was kind of shocked to find out that it was a radio map. So there's a lot of the information is kind of misleading.
So, Bill, you had a comment?
Yes, I would like to say that this attempt to try and justify black holes and relativity theory is in reaction to work such as my own, in which I derive the force of gravity from electrodynamics alone, with none of the assumptions of relativity theory, and I'm able to predict all the data that they have been able to observe that doesn't agree with relativity theory, such as the force of gravity on the outer edges of our galaxy, measured by Pioneer 10 and 11. Also, when you measure the velocity of the outer arms of spiral galaxies, you discover it's too fast for relativity theory and doesn't agree with Newton's universal law of gravitation. But I'm able to predict those things exactly as observed, and I predict them directly from the derivation of the force of gravity from electrodynamics. And the force of gravity is due to the force between vibrating neutral electric multipoles, such as dipoles, quadrupoles, octopoles. And so whenever you have any kind of atoms or matter, you have a mass, and that mass gives rise to the force of gravity. And so the work I've done defines what mass is, but nobody knew what mass was. The closest that you got was in relativity theory. They say E equal mc squared, but what kind of energy is that? It turns out it's electrodynamic energy of vibrating neutral electric multipoles. And Ed Dowdy, who has attended some of our meetings, he while working at NASA, showed that all the so-called black holes aren't supported by the fact when you look at the motion of galaxies near them, they don't follow the pattern they should follow if you have a massive black hole. And so you've got all these contradictions, and they're trying to forget about some of them and develop new theories and new data for supporting black holes. So that's the kind of thing we're facing in science, and you need to dig deeper to find out the secrets that they're not revealing to you that even Einstein talked about, and that is there's politics going on, and there's some political goals in science that are not being mentioned.
All right, so Michael, you have flag up.
Well, in my model, which is ether plus creation, black holes were originally creational conduits for antimatter, and that eventually, after this body of antimatter was created, to get rid of the antimatter to avoid interfering with the new quantum universe, then matter starts to interact at the horizon.
She should call and try.
What?
If she wants it,
and you get.
should she call and try?
Yeah. Then hold on. All right, we'll look at it after you get back.
Well, I just thought she doesn't even have to wait for your 2 hours if she wants to at least ask him about $500.
Okay, it looks like Cornelius is here, so.
And so you get at the event horizon, you get interactions with ordinary matter, but basically it's antimatter in my ether creation model.
So you're saying black holes are antimatter? Is that what you're saying? I can really follow that.
Well, creationally, yes, that's originally what it's made of. But you get these interactions at the surface with ordinary matter later on, which makes it look like it's some kind of dense gravitational body, but it's actually basically it's antimatter, which was creationally the focus of getting rid of the antimatter, so it wouldn't interfere with the creation of a quantum universe.
So here, Harry, I found a picture with a scale on it.
Yay!
Apparently, there's 4 different pictures.
Yeah, there's supposedly pictures taken at different times. There's a lot of jiggling around of the data. And if you look at the paper, I mean, I just briefly looked at it and I couldn't make any sense out of it. It was just, it's like, most of the paper is including the names of all the people who worked on the project, and that goes on for a couple of pages. And then they got references on top of references. And it's just a lot of data points, and they don't even include the final picture in the report.
Now, one thing I was reading about is that, you notice the ring here actually isn't circular. It's actually egg-shaped. And so one of our other fellow researchers, Laurie Gardia, who we've had here before, he basically claims that everything has got this pear shape because of the Mandelbrot fractal influence. So she was
well, it's not really clear to me. To me, this picture, here's the thing. If you look at M87, if you know anything about M87, M87's been in the news for 50 years. It's a pretty famous galaxy. It's been very thoroughly studied. And there's this jet in the nucleus of M87. There's a jet coming out of M87. That's a famous photograph. And there's, quote, knots in the jet. Okay. And people claim the knots in the jet are moving at superluminal velocities. There was a controversy a number of years ago about that. The question in my mind is that jet doesn't come directly towards us. There's a picture of the jet. So it's going out to the side. Why isn't this ring an ellipse?
Well, I think it is an ellipse. It's clearly egg-shaped. It's clearly not.
The jet is going out towards the side. Go back to the jet. Move it down. Oh, there's the jet there. Okay, that's pointing kind of off to the side, but the ring that they're showing isn't tilted. So did they tilt that ring or what?
I don't know. Who knows what they did? What is this thing here?
So I'm thinking that if the jet is coming out of the center of it, and you'll notice in some of the pictures where they show the black holes producing jets, the jet comes out along the axis of it that it's spinning. Okay, well, the M87 jet is not this ring. It looks to me like the ring is, we're looking face on the ring. I don't see the ring is tilted. Why isn't it tilted?
Well, I think it probably is because the shape clearly is elliptical and not circular. If you were looking at it straight on.
I don't see any elliptical. What I see is a ring.
Really? I mean, this whole thing is clearly asymmetric. So, I mean, it's much brighter on the bottom and much lighter on the top. That's far from being symmetric. So that could be just tilted over. And we're just
but it looks to me like it's tilted in the wrong direction.
Well, that would just be a matter of which way you rotate the picture, I suppose. I mean, maybe
they
just
didn't tell me that. So that's another reason to be skeptical of what they published.
Because when you take a picture of something, object out in space, I mean, which end is up? That could be anything.
Well, they didn't tell me whether they processed it to make it to reorient the thing so that it's head on or not. So I'm looking through their report trying to figure out how they processed the picture. Did they process it so that it's, instead of being oriented, we're looking at it face on, or is this an unprocessed? So I don't know. So, I mean, to me, the more questions I ask, then the fewer the answers they have to answer. It's just, to me, it's just.
So there's a picture of MA through normal optical telescope. As galaxies goes, it seems like it's probably a relatively young one because it doesn't have any structure. It doesn't even appear to have a disk.
Well, since I don't know what causes disk, and they don't know what causes radio emission, and they don't really know anything at all really about the physics of what goes on inside galaxies, And what they do think they know has produced the fact that they've got missing mass, and so they don't really have the basic fundamental gravitational dynamics of what's going on in a galaxy. They don't seem to be able to have that correct. So it seems to me like it's all just it's a nice picture, but I don't know that I should accept that black holes exist because you say so.
Well, it is an interesting piece of evidence, though. That's how we do science. People with theories, people do experiments. They thought they could see this thing, and indeed they managed to see something. So, I mean, even as skeptics, we have to, be able to accept something that's reasonable.
Well, basically the issue here is that it looks like a lot of other things that you see. It looks a lot like a planetary nebula. Looks like a supernova remnant observed with a very low resolution.
I mean, what's surprising here? So this picture here compares that image to our solar system, and they show, the orbit of Pluto. It's like just barely a quarter of the way across, and like the current location of Voyager would kind of be way outside the solar system. So to your point that, well, maybe this is just a collection of a donut-shaped collection of stars. I don't know. Maybe it could be. Although there is a
radio
out of it. So
they're measuring radio at at millimeter wave frequencies. So they're, but it's just, I think it made a big splash in the press, and I think that's what the purpose was.
I mean, a black hole the size of our solar system would be, I don't know, kind of unthinkable, right? But
if you knew how big a black hole was supposed to be, then it might be a little more.
I thought black holes were supposed to be relatively small, no matter how massive they were.
Correct. This is a supermassive black hole.
This black hole has been disproven by Ed Dowdy, because what he did is he looked at the orbits for the last 50 years of stars that are nearby this black hole, and they don't reflect the mass of the black hole. So that extreme mass is not there, is what they're saying. And Ed Dowdy's now retired and from NASA, and it's not politically correct to keep saying this stuff. They want certain outcomes in science, and so.
Well, I think the point, Bill, is that as I have books that go back to the 1960s. They call these supermassive objects. They were called supermassive objects. There was a lot of speculation about what they were, whether they were supermassive neutron stars. There was a lot of speculation. They didn't use the term black hole. The point is that the black hole, calling them supermassive black holes, kind of originated around 2000. And then they started calling them supermassive black holes. Well, that was just a change in the name. So all we're really talking about is a name that implies that there's something, because the term black hole is, has a physical meaning. You understand what I'm saying? Black hole has the idea that it has an event horizon and it's a collapsed, it's a hole in space, basically. And so it's black hole implies it's a hole in space. So, but that may not be what it is, but they put that name on it. And so it has become what the name attached to it is. And now they're saying that they photographed the event horizon of a black hole, when in effect, basically, they don't know what that thing is, but they're calling it a black hole anyway. Does that make sense, what I just said to you?
Yes, and this is really part of my concern as well. I mean, I'm rather skeptical about these projects. I suppose it's a bit conspiratorial, but I'm rather wondering if they hadn't specified a name at the beginning of the project. You go out and find a black hole. You know, that is really one of our key performance indicators. And I mean, I'm looking at the way modern business operates, and you sort of get an order from on high. And I'm just wondering if that didn't really influence their whole process, and it wasn't purely scientific.
Well, I think it's scientific. That's the issue is they measured something. They made an image of something that they were expecting to find based on a complicated procedure for processing the data, and then it comes out and they say, well, it's a black hole candidate, and then the press gets it and they say it's an image of a black hole. And then when I first heard about this, the people were talking about it on the radio, and it was obvious that these people on the radio had not a clue what they were talking about. And so, you know, and so you have people who don't know what it is publishing newspaper articles about it and not really understanding. And then the next thing you know, everybody goes, oh, they made a photograph of a black hole. And, you know, and then that was kind of the, you know, and I'm thinking, what?
Well, that certainly is another point. I mean, the popular media do misinterpret things quite substantially, and they give very incorrect accounts. But these tend not to be immediately contradicted by the scientists. I mean, they don't come out and say, look, what appeared in the front of the paper that yesterday was completely incorrect. It's a misunderstanding, and let us try to explain it. They let it go, and it sort of gets legs and you know, just becomes a story which is accepted by everybody. So it's a bit of both, I suppose. It's the sensationalism of the media, which is largely responsible for the second process. But I'm just worried about the first process where, you know, these scientists really realized that it would be excellent in their career if they could photograph, to use the word, a black hole. And it was sort of something in the back of their minds that the whole project was really aimed at doing. So it's really one and the other. The two are feeding each other, and one is not contradicting the other. I've experienced it myself. I mean, you probably all have professionally. You know, maybe I've had some sort of project or something, or I described some paper, and then it might have appeared in the media, and it was completely misunderstood. I'm sure that's quite common.
Okay, I think we beat this subject to death, Franklin. I just wanted to talk about this because, you know, when I was on the astronomy site, there was a guy there who, you know, processed the photograph that was published and said that he ran it through an algorithm and came to a, you know, and saw something that was there, and then people were arguing about it. And it was pretty clear to me that people really didn't understand what it was that the image was to begin with. And so here you have people arguing about what the, you know, what the image was and what was in the image or not in the image. And they didn't really even, and, you know, so the whole thing is like, it's more, I think there's just some misinformation, and I just wanted to comment on that.
So you think even within the researchers themselves, they're kind of bickering as to what they're seeing there?
Well, this one guy claimed that he was able to find a luminosity at the center of the hole. Okay, he used a processing, so he took the image that they published, and then claimed that there was some luminosity there at the center of the hole after he had done processing it. And then all, you know, people started arguing, oh no, that was just an artifact, that doesn't really exist. You know, and he's claiming that no, there really isn't dark at the center of the hole because he had a processing algorithm that he was able to use the data and show that there was something at the center of the hole that they didn't find, and et cetera, et cetera, et cetera. And, you know, and they're arguing about it. And I'm like looking at this and I'm thinking, you know, they don't even understand how this thing was processed to begin with. And now they're trying to draw conclusions one way or the other about what it is, what's in the image. And as far as I could see, there's really not much in the image other than, you know, some vague bright hot spots and some vague hint that there's a circular ring.
Well, I would just be concerned if they just process. I think it would be legitimate to process the image, the data, as long as you do it consistently and you're not cherry picking. See, I would be concerned about them processing data in such a way that they are cherry picking, so that they're just picking the data which looks like the thing that they're looking for exactly, and erasing anything that doesn't. You know, like if there was some bright spot in the middle that maybe someone just went and said, "Oh, that doesn't belong," so we're just gonna erase that spot with an eraser, and just keep this up.
It's kind of a low. You don't really know whether that's why is it bright on one side and not bright on the other. There seem to be 3 hot spots, vaguely maybe 3, maybe not, maybe only 2. I mean, it's just, what can you say?
And look at the cast of thousands who are involved in this project, right?
Okay, can we move on? Let's talk about the magnetic field in the tube.
Well, I think Cornelius is here, and I think we were going to give him a chance to help explain his theory. His theories, which has a lot to do with tensions. So,
well, that's Faraday's claim. Okay, I mean, there's nothing new about this. I mean, this is Faraday's theory.
Okay, is it? I didn't hear about
Faraday's theory is lines of force.
No, I don't think so. So Cornelius,
you don't know anything, Franklin. So just let's,
just hear what Cornelius has to say.
You don't think so? I mean, you're supposed to be a moderator. You're not supposed to express your opinion, and you don't know what you're talking about.
Well, that could be. That's why we're all here.
You're skeptical. You say, I mean, we've been talking about this for a long time. I mean, Bill's talked about this. I mean, God knows how many times Bill's talked about the tension of the fields. They're unbreakable, according to what Bill says. And you just keep, it's like you're not even listening.
Oh, no, I listen. I know exactly what he's talking about.
I'm pointing out basically that Faraday originally had this idea about the field. Okay, this whole idea of field lines and the propagation along the lines of the field, the tension fields.
Let's look that up here. Field, if I could spell field. Field line. Let's see.
I thought we were going to have Cornelius talk about it.
We were, but
I put out a publication, as you may recall, several weeks ago about this. And it kind of like nobody wanted to talk about it. They just wanted to sort of like make it go away.
Cornelius, of course, at our request, sent some of the recordings to Harry and to Franklin and to myself. I don't know if you've listened to those. I listened to them. Some of the quality wasn't so marvelous, but some of it was Cornelius trying to explain some of his ideas about tension. The other was a recording, dealing with the Hubble constant and things like that. I don't know if I gleaned very much from the recordings, although they are useful to archive. I don't know if anybody else listened to them.
I tried to, but I couldn't really. The recording quality wasn't very good.
Yes.
Yeah, I'm surprised since it should have been okay, since all this stuff is done on the internet. But actually, maybe I was going to go and see whether I could actually dig that up. So wasn't very good. So yeah, wondering what happened to Cornelius there. I was going to give him his chance here, but let's see here. We got some things. Yes, we've been quite active though in the emails about magnetic attraction and repulsion here. I'm trying to find, though, the recording here.
Well, Cornelius isn't here, so I guess he can't talk about his theory since he's not here.
Unless we want to talk about his theory in the way that we've heard about it.
Well, generally the argument is that as I understand it, is that you can't have a tension field, okay? And there are people, there's some, and my point is that this idea sort of basically originates with Faraday, okay? And he was trying to, hit the whole idea of field lines, okay, and which, that all comes out of Faraday. Now, the problem with Faraday is it's really kind of hard when you go back and you read what he says. It's really kind of hard to understand what he's talking about. And so that makes it kind of difficult to really comprehend all this. But his idea was that the actions of electricity and magnetism, and then later he sort of tried to extend that idea to gravity, occurred in space. Okay, that it was in space itself, not in the object. So in other words, the forces that exist, what we would call forces, don't exist between the charges. They exist in the field between the charges. And this idea was taken up by Maxwell, okay? And Maxwell gave it the formulation of an ether, okay? He tried to formulate this idea of the field, the action of the field outside of the charges, if you will, was an action in the ether, because he said it had to, because in those days they were thinking in terms of ether. And so Maxwell developed this theory of electricity and magnetism where the actions of electricity and magnetism occurred in the ether field.
So that all seems perfectly reasonable to me. So what happened to that idea?
Well, as you well know, that sort of ran into the difficulty that you guys are running into now, which is nobody was able to actually explain how electric and magnetic fields exist in this ether.
So yeah, we've been discussing there's a couple possibilities. So Cornelius,
Maxwell's formulation had to do with the gear wheel formulation, or he had electric particles and magnetic particles, and they were kind of interlocked, and that the actions of the electricity and magnetism were related to the actions in this ether that Maxwell postulated. And to a certain extent, what David Toome says is an extension of the Maxwell ether idea, where you have these spinning, okay, the magnetic part is twirling, okay, and the electric part is kind of a stress in the medium.
Let's see here. Let's see if we can look up something about what Maxwell thought of, because he's got this kind of, like you said, gear kind of thing. I think there's some pictures of this, but look it up. I can't seem to find it at the moment here.
Well, suffice it to say that the problem with all the ether theories, of any ether theory whatsoever, and it's sort of, Einstein sort of said, well, let's just dispense with the ether, and because nobody had really successfully been able to come up with a theory of the ether that really worked that well. There were all these problems, and there still exist all these problems. I guess they just sort of decided that, we don't need an ether, and let's just go along with Einstein and just say there's no ether, and and we can just redo all of electromagnetic theory and we won't have an ether in it. And they sort of did that, and it sort of looked like it worked, and so that's what they put in the textbooks.
But that's kind of just this whole like things that we don't know about we call black. And generally speaking, there's still no agreement on how any of these forces work, like gravity, charge, magnetism, which is why I think that's why we tend to discuss those things a lot here in this forum, because it's up for grabs, right? Someone could possibly figure out what that stuff is. And so between Akimbo, David, Cornelius, and me, we've been discussing various possibilities. Specifically, right now we're discussing the nature of the magnetic field and how is it that two parallel wires carrying current in the same directions attract, and then if they're going in the opposite ways, how does that repel?
Well, as I pointed out, that's an incorrect circuit diagram. The real correct question is that the currents are in opposite directions, not in the same direction. So that was a mistake that got created by that guy Simony, and that's an erroneous problem.
No, I mean it's a physical, experimentally measured thing. You can have two wires, and the current can either be running in the same direction, or you can run it in opposite directions.
I pointed this out on several times. You're basically trying to solve a problem based on a situation that is unrealistic.
No, it's not realistic. If you take two wires, you put next to each other, and
how do you get two wires and put them next to each other? How do you put two wires next to each other?
You just put them right next to each other. You just take two copper wires.
How do you do that?
You just put them right next to each other. You stick it on a table. You put them an inch apart from each other.
Well, what do you do? Do you have two separate batteries or what?
No, it doesn't matter. It doesn't matter what the source of the current is.
It doesn't matter what the source of the current is, and it doesn't matter what the circuit is?
No, it doesn't. All that matters is that there's...
Well, I claim that it does, because we know that you can't get the force on an electric circuit unless you integrate completely around the circuit. So you have to include the whole circuit in order to get the force on the circuit. You can't talk about the force on just a small part of the circuit.
No, physically you can run the experiment and you can see that the wires will either spread apart or they'll come together. That's what they'll do. That's something you can physically observe. I mean, you can literally do this with wires and batteries, so it shouldn't be a problem to do that.
You don't know what you're talking about, Franklin. I mean, that's the whole problem with these discussions. You don't know what you're talking about, and you're not starting from a well-defined situation. And then now you're talking about something, two parallel wires. Well, I've seen the picture, and they're not a complete circuit. There's just a hypothetical two wire elements hypothetically placed near each other, and there's that. That's exactly it. That's not anything. That's not an experiment. That's an idealization.
No, that can be an actual experiment.
Well, you're just talking nonsense, Franklin. All of these discussions that we have just always devolve into nonsense because you talk nonsense. You have to have a complete circuit to calculate the force.
Force is dependent upon the magnetic field. Well, this is like, the magnetic force expression. F equals QVB sine theta. Okay, so given any current, and you don't have to integrate it.
Why are you putting up these pictures that, you persist in justifying your erroneous ideas by going on the internet and finding erroneous ideas on the internet to justify your erroneous ideas. Why do you do that?
Because this is clearly not erroneous. This is clearly from a reputable source here, from reputable university. So anything I show from hyperphysics does represent the best.
Well, what makes you think they know what they're talking about?
Well, they are the main scientists, and for empirically
So now you're
derived
defending
science,
mainstream science. Okay, go
yes,
ahead.
when it comes to the actual empirical formulas derived from experiments, these things are clearly true. Now, their interpretations might still be completely whacked, but if they have a formula here that says force equals charge and velocity times the magnetic field, depending upon the angle, then I think we can pretty much rely on that. So yes, I mean, what I do when I explain things, I refer to.
Oh, really? Where's the rest of the circuit
science,
there?
and
I
it is
see a
not
wire. I see a wire between two magnets. I don't see a source of electricity or a source of current in it or anything. So to me, that's just an idealization that appears in textbooks where they try to tell you how they think it can be calculated. The force can be calculated. But as we know, there's all kinds of problems that arise with this method that they're talking about. And we know that as in electrical engineering that you have to, be careful about how you do these calculations.
Well, I think you're mistaken about the force between two wires. Definitely that occurs.
How am I mistaken?
Definitely that is.
So you're asserting I'm mistaken. Where am I mistaken?
That this picture is incorrect. You are incorrect in that assertion.
No, I said you need to know what the rest of you need to know where the circuits came from and what the entire circuit is. You just can't show me two circuit elements and say, oh, okay, that's a circuit. No, it doesn't work that way.
Well, they have formulas here. You can plug in the current and you can plug in.
All right, I'm sorry, Franklin. Talking with you is like a black hole of understanding. You don't understand anything that you're talking about. Okay.
And you can see that the force per meter, and this is a force per meter, so you don't have to include the entire circuit, is this 0.00 blah blah 1818 newtons per meter. So that's a physical force that you could measure between these two wires having this amount of current going through them.
Yes, but you have to know how the wires are connected to the rest of the circuit, Franklin.
No, apparently you do not. For this calculation,
I'm sorry. You don't understand electricity and magnetism at all, which goes back to Bill Bennett's comment that all these discussions are just prattle over pet theories that go nowhere. Okay, so all this discussion about what magnetism is, you don't really know. Okay, and you're talking about you've got a theory and you think you're going to explain magnetism. You don't know anything about magnetism, Franklin. Okay, and
yes,
you're
do have this stuff. And if you're dismissing what's on hyperphysics here, then you're dismissing all of conventional.
I'm not dismissing it, Franklin. I'm saying you don't know what you're talking about because you don't understand it.
I understand this stuff perfectly well. Now, the calculation does say it applies only to long straight wires, so that's somewhat idealized, but it's least useful for estimating forces, which it is, and that these forces will arise. It's not like they don't arise. You're kind of claiming that these forces don't arise.
I didn't say that, Franklin. I didn't say that at all. See, now you're misinterpreting what I'm saying. What I'm saying is you have to do the calculations in a complete circuit. You have to take all of those forces. Okay, you just can't take two little pieces of wire and calculate the force between them to get the total force. You have to do the whole circuit.
That's a real nitpick, in my opinion. I mean, whether
no, it's not a nitpick, Franklin.
It is a nitpick. The problem is, is if you do the experiment, do the wires attract, do the wires repel. That's the only thing that's really important here. That's like saying that you can't do that because you have to calculate to like the 6th decimal point to be right. And like technically that's true, but the only observation that we really care about is whether it's attracting, whether it's repelling, and the thing that we're debating.
Okay, yeah, and based on that, what you're going to do is you're going to say, oh, okay, here's my little theory, and I'm going to prove my theory based on this tiny little part of a calculation that you've assumed is true.
It's not even a calculation. All we're looking for is the bulk reaction of the wires.
So now we're talking about the bulk reaction of the wires where we're only talking about a differential force between two little tiny parts of the wire. So now you changed your whole topic. Now you're talking about the bulk force.
We're talking about the action of the magnetic force, whether to attract or to
Franklin,
repel.
you don't know what you're talking about. Let's just talk about something else.
No, I don't know why you say that. I totally know what I'm talking about.
You don't, Franklin. You don't understand any of this, and you just prattle on in your lack of understanding of physics. Okay, you don't understand it, so let's just not talk about it.
Well, I'd be curious, other people are listening to this. It's like, is Harry's criticism that I don't know what I'm talking about?
Franklin, please don't do that. Please, it's not a question of who having a vote as to who's right or wrong. Okay.
Well, that's
not a vote.
actually what science is. Science is everyone has got to get
We're
to
going to have a vote.
opinion.
What's right? What's wrong?
That's right. Everyone gets to express their opinion.
What I'm saying, Franklin, is that you're basing your theory on
I'm basing my theory
really,
on
you're not
science.
taking the whole situation into account. I don't know what those two wires are. If you have two separate batteries in two separate circuits, and then you try to put them together, yes, they're going to do what that little calculation shows. Okay.
And that's
I would agree
fine.
with that. But that's okay. But what does that tell us?
It tells us it generates magnetic forces.
Well, first off, nobody really knows what a magnetic force is actually. Okay. And so you're prattling on about something that.
But we know when they're present. We definitely know when they're present. We can characterize them. We can run experiments. We can definitely identify when magnetic fields are present. And in these experiments, we would definitely identify magnetic field is present. We would check that box.
And how are you going to do that?
By testing it with other fields, which we know are magnetic. You could see the.
You're going to get out a compass needle and say, oh, there's a magnetic field there because I have a compass needle.
Yes, that's exactly how we do it. That is the one good way to detect whether magnetic field is present. Okay. Versus electrostatic field or versus gravitational field. But that's how you do science, Harry.
Well, you don't know anything about it, Franklin, from everything that you say.
No, I know everything is about it. Everything I just said makes perfect sense.
Franklin, you when people show you that you're wrong, you cannot accept it. And that's one of the worst things about you is it just, I'm sorry, it's just unacceptable. Just move on to another topic.
Largely because they don't show me that I'm actually wrong.
Well, you can't accept that you're wrong, and you don't realize that you don't know what you're talking about. You just prattle on. And that's what's wrong with this whole discussion that we're having.
Once again, we're getting into this. We're getting into the discussion between me and Harry. So let's talk about something else. So
I've suggested that a couple of times.
Since there's no point in continuing on here. So, okay, so who else has another topic they'd like to talk about?
I see Cornelius is back. Did we want to say something about Cornelius' theory or his presentation or something? What was that idea?
Well, I don't see him on the list currently. We were kind of hoping he'd come back. He was earlier. And no, actually, Cornelius 2. I see you there. Cornelius, are you here?
Yeah, I'm back.
Okay, so please save us from me and Harry arguing. We were interested in hearing about your theory.
Well, you have to go much farther back than magnetic theory because that's one of the most complex processes there is, and that to discuss that doesn't seem like it's going to be very fruitful at this point. I've described the process in a couple emails recently. I don't know that you've responded or not, but basically it's pretty much what you described, Franklin. The magnetic field does wrap around the wire, and if you have two wires parallel to each other, the magnetic field will wrap around both, and it will attract them together if the current is flowing in the same direction. Going beyond that,
so why is that, Cornelius? Why is wrapping around going to cause them to attract?
Because all forces are tension forces, and so if you wrap a tension around two items, two objects or two fields, those fields are going to attract each other. And
How do you
basically,
wrap tension around two objects? That's
well,
hard.
let's say you're starting at the top of the pyramid instead of starting at the base. You got to start at the base, and that goes back to what's attraction in the first place and what causes attraction, and how does attraction and tension behave.
Well, let's go back to the very beginning then. I would say the simplest thing might be a positron and electron separated by 1 inch. So if you were to create a situation like that, you would find them spontaneously moving towards each other.
Okay, let's go back to a positron and an electron, the simplest thing in the world. A positron, an electron is a rotating, is a focused tension wave that has about it, it's resonant to a point. It has circling about it a transverse wave propagating on top of each one of the tension waves, each one of the longitudinal tension waves.
Well, here, are we talking about tension? Or are we talking about waves? Those are two physical different things.
We're talking about waves of tension. You wanted to go back.
That's a confusion because normally tension is considered something which is, say, static. It's like if you take a steel rod and you twist it, they say that there's a tension, but they wouldn't say there's a wave through it. So what do you mean by tension wave?
So if I take a steel rod that's not tensioned, and I tension that steel rod, okay?
Yeah, you can twist it or stretch it, something like that.
And what happens? I'm taking a rod that's not tensioned, and I'm tensioning it, right?
Sure.
Sure, no problem. What did I just do? What did I just do, Franklin? I just changed it from non-tensioned to tensioned.
Yeah, I totally get that. So that's good.
Did that tension happen instantly throughout the entire rod?
Perhaps not. So the wave you're talking about is the
tension wave, a tension wave, right?
So if I take a bar, like a 10-foot steel bar, and I attach one end to a concrete wall, and then I pull on one end so that the tension cannot instantaneously transmit through the whole bar, but you're talking about the wave of the tension, because physically inside the bar you could see the atoms of the bar actually get wider. That's kind of what it means to be tensioned. And the wave you're talking about is the one that goes from your hand pulling to the wall, which is not instantaneous. So is that what you're talking about? Correct. I can get that.
Okay. So did we just describe a tension wave?
Yeah, I can understand that as a tension wave.
All right, we have a tension wave.
Given that, then how do you? So go on with your explanation. So we know now that we know what a tension wave is.
Okay. Now you don't know what the tension wave is yet.
Cornelius, are you talking about like a stretch string or a rubber band?
That's the way you can look at it. You have to look at something that's tension if you want to visualize it. But I'm talking about the tension.
About a stretched membrane or a stretched string or something that has a force of tension in it.
Or a stretched ether.
Okay.
Or a tensioned ether.
Well, that seems perfectly reasonable.
Okay. So far, we've been talking about tension in a steel rod, tension in a string, things that have atoms, molecules, etc. Okay, so what if we take this tensioned rod tension and make it one atom wide? Okay.
So you have one atom you're going to tension.
Yeah, so basically we have an atom here, and the atom is actually nothing more than a pattern of waves.
Okay, I think we just have to accept that, right? So
and this is another pattern here of waves.
Let's see, are you showing a picture? Let's see, are you, you have a camera on? Let's see here. No? What? So I just wanted to know if you're showing us a picture or something.
Well, are you looking at this? Is my video up?
No, your video is not up. Your camera is not on. So that's what I was wondering.
I can see it.
Okay,
Yeah, I can see it.
Let me turn. Let's see here.
I can see it as well.
Looks
Okay.
good.
Yeah.
All right. So we're going to start. This is not an electron. This is not a positron. This is a wave pattern that would be a neutron and a neutron. Okay, and the wave patterns that are basically the shorter wave distances, and as we get farther apart, we get longer and longer wave distances. We've discussed that before, Franklin. Okay, years ago, 4 years ago, I've mentioned it several times. It's a very important thing that the wavelengths change over distance. Okay.
Explain that to me. I'm a little bit distracted here because I can't see your picture. I don't show why.
It should be basically my camera that would normally be looking at me, but just looking at a piece of paper instead of me. So
yeah, I'm
wavelength changes because the tension is changing.
Because the distribution is changing, of course, because you have less energy because it's distributed over a larger area. And we also know that less energy equates to longer wavelengths. Okay, so the wavelength is longer because the energy is reduced. The energy is reduced. Now, these are circular waves that I'm showing, but in actuality, they would be spherical waves, right? Because we live in a three-dimensional world, not a two-dimensional piece of paper. Okay,
well, I'm sorry here, but it seems to me that the tension in the field has to be decreasing as you go away from the source.
It is.
Okay. So that's why the wavelengths are getting longer.
Yeah. The tension in this area here is much less than the tension in this same size area here, because simply the tension is distributed over a much larger area, right? So, oops, now I see Franklin, I guess. Okay, my image is back up.
Okay, now I can see your image finally.
Okay.
Something was wrong with me.
All right, so basically we'll go back to something a little simpler. We're going to go back to a bubble. Franklin likes this because he likes anything that you can describe with Cheerios, as I recall from 4 years ago conversation that you got the recording of, right, Franklin?
I like to describe anything you can describe on a billiard ball table, but Cheerios is good, just physical.
Okay. Well, you actually said that 4 years ago in 2015, that you like anything you could describe with Cheerios. Okay. So this is the surface of a bubble. If you can imagine looking at it on edgewise on in surface tension. Okay. And if I put over here another bubble, okay, just by me having those bubbles on that surface, the tension increases and decreases over that surface. This would probably be like an area of greatest tension in here and reduced tension here. Okay, you see why that would be? I mean, if you got a surface tension, that's the whole idea about meniscus and stuff. The tension distribution is differently distributed on there. What happens is when you get these two surfaces tensions close enough together, they will start sensing the tension. Tension will redistribute to minimize the amount of tension on that surface. Is that kind of commonsensical to anybody? That so if that's going to happen, in order for the tension to minimize, what happens is these will move. This one will move, this tension area will move toward that tension area, and this tension area will move towards that tension area.
Now, I must admit that I've just never really quite understood why that happens, and maybe that's probably the difficulties I have with this, in that, because we're talking about tension like what you might find in a steel rod, and I can totally understand that.
Now we don't want to go to
We have-
let's not go back to steel rod because that's far too complicated. We need to understand how tension works to begin with. And we've got the bubble here, but bubbles don't end instantaneously like here and here, right? The tension gradually, and so this guy's tension is not down to absolute nominal tension. Even in between here, there's still tension. So if I exaggerate it, there's tension in here. So this surface out here, this is still above that surface. This surface here is higher than this surface of the rest of this container. Okay, and the closer they move, the higher this gets. So as they move closer, we get something that's more like that.
Now the thing is that the way we're using tension, so typically this is called like surface tension, is what.
Correct. Correct. This is surface tension.
Call that.
And I'm using surface tension because we can see the behavior of the tension in the surface. We can see what happens because of the tension surface. Now, what's happening here because of this tension surface is this tension is attempting to relieve itself and minimize the tension, but it's got an air bubble under here, creating that tension. And if you follow this along, because this no matter how far apart these two are, if they're really far apart, then this area here in between will not be, it will almost be back to the normal of the surface, right? But as they move closer,
I'm not quite sure that actual bubbles do this. Like if I have two bubbles in the bathtub, I don't know that I've seen them actually do that behavior.
Okay,
but I've seen Cheerios do that particular behavior. You have Cheerios floating on milk, and I think you brought that up originally. That you do.
No, actually, yeah. Okay, so the only difference is if I have Cheerios floating on milk, here's a Cheerio here.
I mean,
the only difference is that when I have a Cheerio and I look at the side of a Cheerio, okay, this is my Cheerio, right? If I look at the side of the Cheerio, I have a meniscus that follows, because it's attractive to the water, I have a meniscus that pulls up onto the edge of that, up onto the edge of that Cheerio. So it's still got the same curvature to it, but it's just that the Cheerio is causing the curvature by attracting the water up towards it instead of the air bubble underneath the water causing the curvature. We're just trying to create the surface tension, whether you create it by floating a Cheerio in the surface and the Cheerio is attractive, has a adherence to water and so it goes up, or you could float something in there that is repulsive to water, right? That repels water, and what you got is you get a dip then in the around where the water is repelled. So therefore, instead of pulling up onto the surface, it pushes down. And so you've seen those things, right? Where you can float something on the surface of the water and it'll like push it down away from the object, or if it's coherent, not coherent, but adhesive, then the water will pull up on it. You've seen those things. The side of a glass, you see it at the edge of a glass. You see where the water.
Watch the water skier. You can see that their legs are impressing,
right,
denting the water.
Okay, so basically we're just using these objects to create the surface tension. Here we're using a bubble to create surface tension as opposed to a Cheerio. Okay, either way we've got surface tension. The thing is, we're going to talk about the tension, not the bubble, not the Cheerio. We're going to talk about the tension it creates in the surface. Now there's already surface tension, so it's the tension distribution that it's creating. All right, so now let's get back to this. Does everybody see and understand, except for maybe Franklin? You might want to put a couple of bubbles, sit in a bathtub and fart in it or something like that. I don't know. But put some bubbles on the surface of the water, and then observe the bubbles. And you'll notice that as the bubbles get closer together, they'll actually start accelerating towards each other. And I've never measured to see if. But so the closer they are, the faster they accelerate. And that acceleration is kind of like equivalent to a gravitational field. The warpage of the surface tension is like the warpage of a gravitational field. And because that object is creating a warpage, the closer they get, the faster they move together. Now, there's a reason they move together, and that's because the surface is trying to relieve the tension always tries to relieve itself and minimize the tension. And if you look at this area under area A and area A prime, the area under those two bubbles is associated with basically the amount of air in there, right? Portion of that. If you look at when these come together, what happens is, and you could, this is true of any geometry, then when they finally come together, what you get is you get one large bubble. The areas have to add up, A1, A plus A prime. That area adds up, but the surface, the distance from here to here, the surface of that bubble is now smaller than the combined surface of these two bubbles.
So you're just saying that the energy of tension is greater for the bigger bubble, or is it less?
It's less for the bigger bubble because
so we have a case of nature is seeking the lowest energy level.
Correct. And so it's trying to, it basically always, the tension is always going to move where it's easiest for tension to move, and that's to where the tension is less, where the tension moves fastest. Okay.
Okay, so we can accept, we've seen stuff like that. So where are you taking it? So we played it to the positron-electron thing.
You didn't want to jump right into that positron-electron thing. Didn't I tell you? Okay, positron-electron. Here we go. You really want to get into that. I don't know how many times I have to tell you, you're starting at the top of the pyramid. Okay. Neutron. Right? Okay, we started with a bubble here. We haven't even got to the neutron pattern yet, okay? But Franklin wants to go right to the positron-electron. Okay? Okay. Now we got an electron. Egg-shaped. 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 Okay? Revolving egg-shape. Each wave is getting bigger. Okay, now you got to take it. So this wave, this tension wave that's coming inwards here, because it's a tension wave. It's not a compression wave going outwards from the outside. It's a tension wave being pulled in from the inside. See, so I'm stretching here, okay, and that creates the tension wave inwards. Okay, tension is going to, if I stretch a rod, then as I tension that rod this way and this way, the rod has a tendency to eventually weaken and neck. Okay? This is me stretching not a rod, but a three-dimensional surface, three-dimensional area being pulled on. The tension is going to get eventually, it's going to move where the tension is greatest. It's going to move faster. So it's going to move towards the center. And then as it gets towards the center, it's going to weaken that material. So it has to slow down because tension moves slower in a weaker bonded surface, a weaker bonded material. So if it moves slower, these waves are going to get shorter. See, I was showing you earlier that the waves are longer, getting longer and longer. But we're talking about tension, so the waves aren't really coming out from the point. The tension waves are going in and working their way towards a point because that's where the media, the carrier media, is weakest. Okay, so that's the fundamental neutron. Then they add on top of the neutron, you have to have, okay, a neutron is going to be a spherical tension wave moving in towards a point because this tension is going to eventually create weak spots, and then those weak spots in that field, it's going to focus towards those weak spots because it moves slower towards a weak spot. So if I have a straight wave and it's propagating in that direction, then if it finds a weak spot, it's going to move slower in that direction, and it's going to start moving. And so this is going to move slower. This wave, this area here is going to move faster, and you're going to wind up with a curved wave here because this side of the wave is moving faster, this side of the wave is moving faster, this side is moving slower because it's going towards a weak spot. And that weak spot becomes weaker because there's more tension now getting focused towards it. And eventually that weak spot becomes a self-perpetuating weak spot. And the tension will be focused towards that. So now you've got all right. So now we've created a neutron. Going through this really quickly because we got to get to the positron and electron because we want to get to the top of this pyramid right away without understanding anything in between, right? Because that's the question: is how's the positron and neutron? So now, is everybody okay with just jumping right ahead on this and following this? Fine, right?
Yeah, well, we're okay, but you'll only have about half an hour, so.
Oh, so you want me to put all of physics in a half an hour?
Yes, that's what we'd like you to do.
I'd rather have you tell us where the magnetism and electricity come from.
We got to get to an electron first.
Yeah, let's get to an electron. So what's an electron?
I mean, magnetism and electricity are, you've got to make an electron first, right? Because it's an electromagnetic field. It's not a magnetic field. And it's not an electric field. It's an electromagnetic field. So does everybody understand how a neutron works?
Not exactly. You had the neutron, and it has the tension waves going around it. Were you just showing just the neutron then? Because I thought you were showing the electron.
Well, no. Does an electron has mass, and a neutron has mass. First thing you got to do is before we get to an electron, we have to form a point of mass. Because an electron requires there to be a point of mass for it to form around.
So why were we talking about neutrons?
Because a neutron is the simplest form of mass.
So you think the neutron is fundamental compared to the electron then?
I think a neutron forms first, and then an electron and proton come from that.
Well, that's fine. But I'm still not quite sure what your formulation of the neutron was. Other than it being circles.
It's a bunch of tension waves that move towards each other because the tension gets weaker in the middle, and so because the tension is weaker in the middle, it naturally attracts additional tension.
So it's kind of like a bathroom sink. I mean, like a drain in a tub kind of.
No,
thing.
there's no fluid flow. It's just tension waves.
No fluid flow, but as far as tension goes, there's something flowing towards it, right?
It's waves moving towards the area of the center because like I said, did you catch the part where if you have a straight wave moving this way, right? If there's a weak spot, and eventually there's going to be a weak spot because you would have another wave moving this way, right?
So why would there be weak spots?
Well, because here where the waves meet, there's twice as much tension, right? Because there's tension from this wave and there's tension from this wave moving together, right? That makes sense?
These are your tension waves that get
this tension wave front's moving in that direction. This tension wave front's moving in that direction. And here's where the two are meeting. This is going that way. This is going that way. Here's twice as much tension, right, as there is in the rest of the area.
I don't know. I mean, waves typically just pass right through each other. They don't.
Well, but doesn't the wave get twice as high in amplitude here because this wave crest meets that wave crest? So, it's just like I got this bubble, and then I got this bubble. The area under that. Okay. So the tension is twice as big here. Okay, does that make sense?
Sure.
Okay, if the tension is twice as big, how much can you tension this media before this media breaks? I mean, do you know of any media that you can continuously put more and more tension on, and the tension and the media will not weaken?
None that I know of.
Okay, so we eventually get to where this media, the media starts to break down, so it can't carry as much tension. It has a limit to how much tension it can carry. And if the media can't carry a tension wave, what has to happen to that wave? It can't enter that area where there's too much tension. So if another wave comes along here and it tries to pass through this area, there's too much tension here, and so this is weakened. It's almost like to the point of being broken. So
I would call it more like saturated, I would suppose.
As the media gets weaker and weaker here, okay, as you approach it, as this wave approaches, it's getting into an area where the tension carrying capabilities of that media is becoming weaker and weaker. So therefore, the wave speed is dependent on the ability of the media to carry tension. If the media has a very good ability to carry tension, the wave will move fast. If the media has a poor ability to carry tension, the wave will move slow. Does that make sense?
Well, I would think it would stop. I mean, if it actually loses its ability to carry a wave, then it
okay,
would.
But somewhere in between stopping and moving, there's got to be a region in here where it's gradually getting weaker and weaker, and so it doesn't stop immediately. It gradually enters this area where the media is getting weaker and weaker. So it basically is moving fast. So we got a long wave, and then it starts to move slower because we're approaching that area where it can't be transported as well. So this right here moves slower and slower, right? As it approaches this point here where it's too darn weak to even, I can't even get tension through there because it's almost broken. Or you can say, okay, there's a break in the media there. Okay, I don't want to go there because media will not allow itself to be broken. So that this part of the wave here, it's going over here, and it's going over here. It's going past this region where, okay, here the tension is not as bad here as it is here. Here it's bad because these two waves combine. Well, here it's only this wave we got to deal with, right? So,
okay, so you've motivated a weakness in the tension field. So then that's a neutron?
Yeah, well, it's more than that because it's also a resonant location too, resonant point. But these waves
Standing wave, you mean?
Exactly, it's a standing wave at a focus to a point, but it's self-focusing, right? Because this weak spot here is going to still get some waves coming at it, which is going to weaken it, which is going to maintain it as a weak spot. This spot here, this out here, because this is moving faster, this wavefront doesn't slow down as much as these wavefronts do, as the wavefront does here. We're going to get a curved wave eventually.
Well, Cornelius, as I understand what you're saying, when you say weak spot, you mean a place of minimum energy. Okay, where you showed that the two bubbles move towards each other and coalesce because that's a minimization of energy.
Well, no, it's not the same thing because in this case, the weak spot basically is an area where we can't transport the energy. It's surrounded by a lot of energy.
I mean, it's like your diagram you have on the left where the two bubbles, they join together to create a peak.
Right,
so,
but every time you do that,
if there's a limit to the magnitude, then, you know, it's going to remain the same peak no matter how many bubbles you have down there, I would suppose. Right?
Well, eventually you're going to have a bubble, have it look like this. It's going to get to where, it can't support it, so then we lose it. We lose strength. So if you look down on this, then what you see is that.
So, and that's a neutron.
That's a neutron.
Okay.
It's the weakest spot in the media.
I think you said that the sum of the two areas of the two bubbles would be greater than the integrated bubble earlier.
No, it's not the sum of the area, the sum of the surface area, but not the sum of the volume. The volume of the bubble will be the same. The volume of the air within the bubble will be the same, but the surface area will be less. It's like me taking two squares, Ian, right? If I take two squares or two cubes and I put those two cubes together, I get a cube that's this size, right? Because this area A plus area B is equal to what used to be area A and area B, right?
Yeah.
Oh, I guess I'm seeing your picture instead of mine on my screen. Is everybody else seeing mine?
Well,
I
was
get rid of
both. I guess Ian, you probably want to put your camera down while Cornelius is.
Okay, so here's area A and here is area B. It says these are cubes, cube A, cube B. We're not going to complicate things by working with spheres, but area A and area B are cube A and cube B. If I combine those two cubes, the surface area of the one combined cube is going to be less than the surface area of this cube plus this cube. If you look at squares, like we would look at these squares, this area, this distance here around plus this distance here around is going to be less than this distance here around. Right? If you add the four sides. So the same thing is true of a cube, and the same thing is true of a sphere then. The surface area, so the total area here is the same as A plus B, but the surface area around the surface of what's left is less. And that's the same thing with the bubbles. The surface area is going to be less. Oh, this is a terrible drawing.
Is that important for your theory? I mean, I don't think that would really necessarily matter.
Well, it matters because in this situation here, the tension on the surface is less than the tension created by two individual bubbles. So that's important. We've reduced the tension. And so what happens is that's causing these bubbles to move together. Now, we need to get into go from bubbles and surface tension of bubbles to surface tension of waves. And your favorite thing to say is, well, waves just move through each other, but they don't.
No, my favorite thing, if it's waving, then what's it waving through? That's my favorite thing.
Well, and it's waving through the ether. It's waving through the electromagnetic field. It's waving through space. It's waving through what's between and what creates particles. It's waving. The particles themselves are waves in the ether, in the media, in the carrier.
They're standing waves.
Yeah, well, standing waves, yes, standing waves, because they are resonant. They're resonant to a volumetrically resonant wave.
This is where Franklin doesn't understand what a standing wave is, and you have to
I think Franklin does understand what a standing wave is. I give him credit for that, Harry. I'm not gonna go to the.
I'm not going to accept that because I don't think he does.
Okay, but what we do need to realize is that waves do not just move through each other. Waves do just not pass through each other and go on like they never happily met another wave. We showed that right here. This wave going here and this wave going here affected this wave here. It didn't just allow this wave to just happily transport through this area here without distorting. That wave here all of a sudden became curved because these two waves stressed the carrier media to the point that the carrier media could no longer properly carry this wave in a straight line and keeping it. So they didn't just pass through each other. All of a sudden, this wave became curved. Okay, there's more to it than that. Hyginus is probably where you want to go next. Do you understand the Hyginus principle? Hyginus' description of wave fronts and that?
Well, I would just like to see that demonstrated in like an actual wave pool.
What would you like to see demonstrated?
That waves don't pass through each other. If that can be demonstrated in a wave pool, that would be a more effective physical demonstration. But otherwise, we can only presume it works by what you've postulated, which may not necessarily actually occur.
Is the ocean a big enough wave pool?
Sure.
How did waves get as big as they get?
I don't know, by the wind pushing them, right?
Start out as little ripples, right? But they'll eventually combine, because just like the bubbles combine here, this is the wave here. This is the wave here. The waves are moving in that direction. The same direction, not opposite directions. They're moving the same direction together. See them they're moving together, see? Okay? But this wave is being affected by the tension in this wave. Just like this bubble is affecting the tension in this bubble. And just like these two bubbles combine, if these two wave crests move together in the same direction long enough, they will eventually become a single wave crest.
Yeah, that's cooperative adding of waves. Yes, we understand that.
All right. And once they cooperatively add, do they ever subtract?
Well, you're saying that the carrier isn't a linear medium, basically.
I mean, it is possible. If you have two waves
yeah,
heading
I
in
definitely say the carrier is not a linear medium. I think I've said that multiple times. Non-linear carrier wave, carrier substrate. Non-linear, tensionable non-linear media. Absolutely. But then again, what is really linear in this world?
Well, most of the time when waves pass through each other, we're dealing with linear media.
There's no such thing as a linear media, really. I mean, you go to the extent you just like we said, you could stretch a piece of steel, but you can't stretch it infinitely because it's not linearly stretchable. You can stretch a spring, but you know it's not linearly stretchable. It weakens. It changes its characteristics. It eventually becomes it's no longer elastic. It's plastic. Somebody's got an echo on.
Yeah, we
anyway. Okay. Anyway, that's why we start with trying to understand tension. Then you have to get to tension waves, which we said, well, yeah, you pull on a bar and the wave will move down to tension. And then we get into tension on surface tension, and we get wave following wave moving together, and the two waves combine into a single wave. And from then on, they happily move together as a single wave. They don't separate again because the tension is minimized. That tension keeps them together as a single wave.
But they would have to be going in exactly the same direction. Otherwise, they would separate.
They would separate at a certain point. Some parts of them will. Depends on how. If they're not going exactly the same direction, then
that's still not really an example of like a collision or a reflection.
No, we have nothing to collide against yet. We just have an open surface.
So go on and explain the positron electron thing. I want to make sure you get a chance to explain that.
Well, I'm not going to get to the positron and electron thing by any means. We're still working on trying to get understanding a neutron, right? We have a better understanding of why waves will combine and become a single wave, right? So we have a better understanding of why when these two wave fronts come together, that at this point here now, those two waves will happily move together, even though this part here and this wave here moves ahead in its normal direction. This one here where the wave is combined and the media is weakened, this slows down and it moves together like that. And so it will become a neutron pattern that's actually moving eventually. And any other wave that encounters it will wrap around it, even if it's coming from the other direction. Because this is the weaker area here, this wave will move faster here and slower here, and it will combine and become a part of this, weakening this even more. Okay, so now we've got this weakened area of energy here where the waves can't go through. If the waves can't go through, then I got a wave coming here. Okay, it's going to come enter this area here, and it's going to move slowly here, and it's going to move fast here because here it's not as weak as it is here. Its wave carrying, tension wave carrying capability here is better than it is here. So what happens is this creates this augments this, and this wave starts to move faster. So we wind up with a rotational characteristic, because if it can't absorb any more energy, the best way it can absorb more energy is for this wave crest here to become stronger. And for it to become stronger, it has to start to rotate and become more of a cam shape type thing. And there's a follow-up wave that's coming into, it also becomes cam shaped. But because this one's rotating, each individual lobe of this cam is going to be rotating at a different location depending on how far out on the wave you get. So now we have a rotational wave pattern. And the wave front is going to go to where the wave is weakest, or the wave carrying capability of the media is strongest. And that happens to be okay over here. It's not, because I got this incoming wave here competing with me. And so it says, I'm going to move out of the way and I'm going to go over here, because over here, there's less stress in the media. So that where these two combine, the tension is going to move away from that and move towards here. And that's why it starts rotating. Okay. There's more of a reason, as I think I explained somewhat, I covered that somewhat a little bit last week, where there's a reason they rotate in a single direction only. And that's because all waves within this entire universe are basically, the universe is rotating clockwise, so all wave patterns within it that are forming like this will start to rotate counterclockwise. So that's a much bigger picture there. Okay, but the universe and an electron and a neutron and a proton are not flat objects. So now, if I'm just going to draw one wave pattern here. Maybe got the center of the wave here, and I've got an egg-shaped wave pattern here. Kind of a cam lobe shape, right? And that lobe is as you go out to the next wave, see how the lobe is rotating. So the next lobe, and that'll be because if it was here, you see if that lobe was here, then it would be too close to that one there. There's already a lot of tension there. So it's happier being out here because there's less tension out there. So I can move faster out here. So this wave is rotating around. So we have now the longitudinal waves coming in, and a transverse wave, right? The lobe here is a transverse wave, right? Because it's moving around this direction. So it's a transverse wave rotating around on top of a longitudinal wave. The longitudinal wave is what causes the mass and gravity. The transverse wave is what causes electromagnetism, because mass and gravity. So if I have perfectly spherical waves, then my wave tension from wave to wave, if I just look at the wave crests, this is if I look at from the side, if I look at this wave crest, followed by another wave crest, followed by another wave crest. If I look at this from wave crest to wave crest to wave crest, then I wind up getting an overall picture that looks like this. And so this is gravity, is the tension from wave to wave to wave to wave. If I had a boat sitting on top of this wave, it would have a tendency. Now this is actually, let me draw this upside down. Gravity well. Wave, bigger wave, bigger wave, bigger wave. Not very good. Now I got an object also made of waves, which we won't worry about right now, floating on this surface. But what's happening here is now, if it's a big enough object, it's just sensing multiple wave crests, and so it's going to move down into that well. Okay. So
that's a inverted pressure graph. It's going to be attracted to the higher pressure.
This is the lowest. This is the weakest spot here. This is the center of the neutron. If we're looking down on the neutron, it's here, 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 here. See, these are actually longer waves. I'm drawing them wrong because this is not a shorter wavelength. This is a longer wavelength from here to here. So I've drawn this wrong. It's a long wavelength, and it gets shorter as you get down into the. This is the gravity well. If I have an object riding on top of it, again, these are shorter. If I have an object, and I'm saying object very, very freely here. Objects, however, are themselves patterns of waves. They're not separate from the wave pattern. Anyway, that will go down into the area of weakest tension, because that's where tension goes, where it can't go anymore. I got sidetracked. Where did my other one go? Not sure. That's the wrong one. Oh, okay. Well, I think this is the one we were working on last. But it's not two-dimensional like this. So we have a rotational transverse wave pattern around here on top of this sequence of longitudinal wave patterns. Each longitudinal wave pattern has its own transverse wave rotating around on it. Kind of like it's one cam lobe, another cam lobe, but they're not separate. They're just the waves are moving around in that direction. The tension is moving around in that direction. Okay. Now, the thing is that the tension is going to go, this lobe here is going to move over here because there's no tension over here yet. So if there's no tension there, that means that the tension carrying capabilities, the media is stressed less, so it's the ability for it to carry tension is better over here, so it's going to rotate. The same is true in a three-dimensional world. It's not only going to rotate over here because tension is less. If we start rotating this all the way around, then that tension in that area has over time become greater. So what do? If the tension in this plane is greater, you stand it up on edge, and it has to rotate down into the paper as well. So it precesses, not only this lobe here not only rotates around the center point, but it also precesses down into the center point, underneath it, and back up. So we have a dual rotation. We have a curl situation. Because, and the reason it's moving is because, like I said, it's moving to the point of least tension. If this is greatest tension here, it's going to move to a point of less tension. If it goes completely around in a sphere, that means that the point straight up and point straight down hasn't been stressed by a wave going through it. So it's free for all area. It says, oh, well, straight up and straight down, nobody's bothering me over there. I'm going to go over there where I can travel easier. So that's why it processes. It goes to the location of least resistance to its motion, which is going to be the area where the greatest tensile strength of the material is. Because if you stress a material and it becomes overstressed, it loses tensile strength and starts necking. So if I stress this media in a three-dimensional area, if I stress this over, then it becomes too weak to carry this wave at a fast speed. So it's going to go down to this area where there's less stress, because it gets to go where it moves fastest. It's just like, if I'm going down a highway and the lane over next, the wave is always going to follow the direction of the wave crest, of the wave front, is always going to go where it meets the least resistance and where it can travel the fastest. So if I got a straight wave front here and it's less stressed here than it is here, this wave front is going to have a tendency to curve in that direction. Okay. So it's going to go over here because this is too stressed to carry it. Over here, it's moving faster, so this one is going to move towards that direction where it can move easier. Does that make sense? Okay, so this is...
Yeah, although I'm afraid it's a little bit short on time.
Okay.
So.
Well, you asked for an electron and a proton, and I haven't even got to the proton, and I'm sure that everybody's really trying to put this together in their minds right now about how complex this wave is. So that's why I say you have to start understanding tension. You have to go from a static tension on a surface, to a three-dimensional tension in a three-dimensional media. You have to go to I always lose that one where he's got the, you make a wave crest and you make it out of little waves. What the heck is that? Anybody remember that?
This is the Fourier composition, probably, Cornelius.
No, this is
Huygens principle.
Hyginus made that to where you could take a wave and you can make it in multiple little waves, and that would help you predict how fast that wave front moved, depending on the media it went through. That was Hyginus. If you look up Hyginus principle, you start with this single static point of a bubble. You expand that into a bunch of bubbles in a row, and you look at how those would move based on what is in front of them for the type of stress within the media. The media's ability to carry that tension is what determines how fast that wavefront is. It's the reason that light bends as it enters glass, because so the Hyginus principle tells you that. But it's all about tension, and it's not about particle A and particle B, because particles aren't particles. Particles are wave patterns of tension, and you have to have some connection between particle A and particle B in order for particles to pull. And that fact is the fact is that particle A is part of particle B. And let me draw one more picture. Okay, I think we're done anyway here. I'll draw one more quick picture. I don't know if this is going to work out or not. Okay, what you'll see is that if these waves are getting longer as they get farther out, you'll see that you get to a point eventually where this wave crest here, let me draw one more. is going to be parallel with this wave crest here. I'm not sure you can see that. So these two, this wave crest is moving in that direction, and this wave crest is also moving in that direction. And they're following each other very closely, like we said before. Two waves moving closely together are going to attract each other to minimize the tension. So looking at it from the side, this is the one wave, the leading wave and the trailing wave, both moving in that direction, and they're going to eventually attract each other. And if they attract each other, that means that the distance between this wave crest and this wave crest has become greater, and so it's going to, there's more, it's easier for this one to move ahead because there's less stress, there's more distance here with less stress in there, so this one's going to accelerate. If this one accelerates, it causes this one to accelerate, and if that wave accelerates, it's going to cause this wave to accelerate, et cetera, which means that this wave is going, this point is eventually going to be accelerated in that direction. And the same is true of, the opposite is true of this one. This wave had to slow down a little bit because it's being pulled back by this wave. It was pulled back by this wave. This wave gets pulled back because now this is less distance here. So it's more like, it's easier for it to slow down and travel here. And this wave is that. And all of a sudden you got this center of these waves moves that way. And this center of this wave moves that way because as these waves combine and they feed back through their own respective wave patterns, the centers move together. And
Where can I find more information on it so I can read it during the week?
You just saw all there is.
Yeah, unfortunately, Cornelius, this is probably one of the best presentations that I've seen. I didn't know that it was quite this complicated in the geometry. So.
Yeah, it's very complicated in the geometry, but it's very simple in concept.
Similar to Milo Wolf's books.
Similar to Milo Wolf's books, Milo Wolf does not deal at all with the fact that it's a tension wave. Milo Wolf does not deal with the fact that the wavelengths change over distance. So there's a lot of things, but Milo Wolf was probably 10 years ago or better. I don't know how long ago when I first read any of the Milo Wolf's things. And Milo Wolf's things I struggled with, and I finally came down to it's a solid, it's a tension wave, and there's nothing but waves. There's no such thing as anything discrete from the wave carrier media and the wave pattern within it. All forms of energy come down to tension wave patterns. And like Trenken said, the geometry is complicated. But whether the geometry is complicated or not, the concept is very simple. And from there on, it's just building on that geometry. And we haven't got into the rotation, how the rotational wave patterns interact and how electromagnetics works and all that. We have barely scratched the surface of what an electron even begins to look like.
It's very nice. I wish you'd write it up so I could learn more.
Well, that's just not. If you've read any of my emails and you've seen my stutterings, and you probably know that I'm not a strong documenter. If you can give me a Kleenex and a cup of coffee, I could probably sit there and talk your ear off anytime. But
if you're really interested, you should just I'll put the recording up, and you can just go through and I think if you watched it a few more times, you would probably catch more what he's trying to say.
Yeah, as a matter of fact, that Glenn Baxter recording, I can send that out to other people. Franklin, you would have gotten it too. It's a very poor recording, but it describes some of this.
Okay, but
I'm going to call it quits.
Yeah, if anyone wants that recording, they can ask me. I'll send it to. But I'm afraid we are over time here, so thank you, Cornelius, and I thank you for actually setting up your camera this way so that you could draw and provide the pictures, because really this really is something that really requires pictures since there's so much geometry involved with it. So I think that was very helpful.
Okay, well, thank you. I'm gonna leave the conference now.
Okay, and did you want to come back next week and continue explaining this?
Oh, nope. Next week I'll be on the road. It's Easter.
Oh, it's Easter. Okay, well maybe some other time then.
Yeah,
But thank
maybe.
you.
I said it's gonna have to be a shoot from the hip thing, as you already know. I'm not pre-documented. So
Okay,
you
but
guys
this is great.
have a good holiday.
All right, you too as well. All right, so that will do it for our conference. And so today we had talked about the announcement of the picture or image or radio map of the black hole. And then we had discussed some of the theories of Cornelius Verhey about how he believes tension forms the world. So thanks for everyone for your participation, and we will be doing this again next week, I believe. Okay, so.